conversation starter than anything.
Yeah, brilliant. So thanks very much, Sarah, for standing in at the last minute as well for Jeanette.
Oh no, you're very welcome.
Thanks very much for that. So John arrived, so we can start. Welcome today to Matteo and Sarah, who are going to give us a talk on using large language models to identify metaphorical expressions in text. Over to you.
Nice. All right. Thank you very much, Paul, for the invite, and to you all for joining here today. So this is going to be about like a summary of a recent study that we've done in which we tested the ability of large language models to carry out a task that is really important in linguistics and discourse studies, and that is very often the first thing to do, the starting point of metaphor analysis, namely the task of identifying and annotating metaphorical expressions in text. Now, metaphor is a pervasive feature of language and discourse, and it also provides a useful lens for examining things that have to do with language and discourse in society, such as Elena's work on patients' experiences of cancer or public perceptions of immigration, national identity. So like really big questions that we can tap into through an analysis of metaphorical expressions in text. However, metaphor analysis is also an extremely time-consuming process because there are currently no reliable methods for automating the crucial yet challenging task of identifying metaphorical expressions in text. And the main reason why this is so hard is that metaphor is a very context-sensitive phenomenon. As the simple example shows, some expressions may carry a metaphorical meaning in some contexts, but not in others. And that makes it really tricky because we need intelligent algorithms to be able to separate metaphorical and literal meanings. Now, note that this problem is not limited to metaphor at all, but actually applies to all sorts of pragmatic and discursive phenomena, like speech acts, for example. Even the most formulaic and seemingly predictable expression of apology, the word sorry, does not always perform the pragmatic function of apologizing, as for instance, in cases where someone reports someone else's apology. Evaluation, also referred to as a stance or appraisal or sentiment in NLP, that is another very context-dependent phenomenon, as the same word can have different evaluative meanings in different contexts. And finally, when we get into broader categories of discursive function, then things get even harder. What you see on the slide here is an example of what in critical discourse analysis we would call a discursive act of legitimation, which is the act of defending controversial sort of activities or policies or decisions. In this case, what we're seeing here is a coal company defending the use of coal by highlighting the societal benefits it brings. Now, this kind of stuff is super hard to quantify based on forms, based on words, because what do you count? None of the words in this sentence here does the legitimizing on its own. It's the whole sentence that does. So the problem then is that form-based approaches, which are dominant in corpus linguistics and to some extent in NLP as well, will inevitably be limited because context needs to be taken into account for correct interpretation. We cannot predict in advance all of the possible expressions that might fulfill a particular discursive function, like metaphor, evaluation, or apology, or legitimation. It's impossible to take a bag of words approach, or at least such approach is very limited. And discourse functions can stretch over multiple words. So very rarely is the single word the actual unit. So that's why a lot of metaphor researchers, in most cases, have no choice but to manually annotate their corpora using tools such as NVivo. Now, this is not only a horrible process because it takes hours and hours and hours, and it's really demanding and tedious, but it's also error prone for precisely the same reasons. People get tired, right? So, we've all had, I'm sure, examples of this in our own annotation work, that sometimes you just realize after reading and going through the text one more time in the morning that you missed a few instances, or that you disagree with yourself because God knows what was going on in your head at that time when you were super tired and had been coding for, I don't know, 4 or 5 hours straight. However, can LLMs come to the rescue here? We know that LLMs are incredibly incredibly capable at processing texts, increasingly capable at understanding text, quote unquote understanding text, in a way that really mimics the way humans understand text. They can take context into account. They understand context on some level. They are efficient, obviously humans do. They are extremely flexible in the sense that we can prompt them to do all sorts of things, and more things can be done via LLMs. They are, for this reason, scalable. Another major advantage is that unlike other NLP approaches, they don't require really advanced programming skills beyond being able to run a Jupyter notebook to access the API. But are they accurate? So this is what we wanted to test in this study. Now, of course, we're not the first people to try to automate the task of identifying metaphorical expressions in text. There is, in fact, a long research tradition within natural language processing focusing on this task, which is known as metaphor detection. So people in NLP, as far as we can tell, don't use the term metaphor identification. They use the term metaphor detection. So that's how we found that stream of literature there. So this line of work started well before LLMs, and the traditional standard recipe is to build a supervised machine learning algorithm, typically trained using different features such as part of speech tags, concreteness ratings, lexical resources. So these are auxiliary features that are fed into these models. And then in terms of representing the text, there are different word embedding algorithms, I guess you call them, but you're the experts here that have been used. There are static embeddings like Word2Vec and Glove initially, and then contextualized representations like Bert, Roberta, Elmo, and these. And on a theoretical level, the vast majority of NLP studies that we've come across, and this is an important point for later, typically are based on the metaphor identification procedure, which is a long-standing procedure for identifying a protocol for identifying metaphorical expressions in text that was, I think, the Praglajez group. I can't remember all the people who are in that group, but I think maybe Sarah, you can jump in here. But it's the gold standard so far. It's the mainstream protocol for identifying metaphor in text. And one thing that is very important to keep in mind is that although it doesn't have to be, this protocol is very much based on single words. So it's about going into a text, looking up every single word in that text against a dictionary definition. And if there is a dictionary definition that is more basic than the current definition in that particular context, then we can say, okay, this is a metaphor. Now, this is an important point because what we are going to use is an approach that relaxes this criterion a bit in the sense of allowing, more explicitly allowing metaphorical expressions to spread over multiple words in something that is, I think, more, or we think is more natural, more, if you like, better reflective of the way that humans understand metaphor. But we can come back to this. In any case, the task in NLP studies, and this is another important point, is typically incredibly narrow. So it's most of the time, so far at least, these algorithms are given a sentence decontextualized from its original text, and the algorithm is instructed to class a particular target word as either literal or metaphorical, usually even narrower than that, a specific verb or an adjective. So words belonging to a particular word class. An alternative variant is that a whole sentence is classed as metaphorical or not, or in some cases that each word within that sentence is classed as metaphorical or not. Notice that we're still talking about single sentences out of their original context. These are some of the state-of-the-art results from this line of work. You can see the results are pretty robust, right? These are the there's 2 or 3 data sets that people use all the time. This is, I think, was created by the same people who created a variant of the MIP procedure. So the Amsterdam school, I would call it, of metaphor studies. So people like Gerard Steen and colleagues. So they've created a resource that people in NLP have used time and time again. And then these other data sets are, I can't remember how they were built, but they are, again, collections of sentences. They're not texts. All right. Now, of course, in the past couple of years, LLMs have started to take over the field more and more. And so it's only natural that people have started experimenting with them in NLP. Here are a few results. People have used LLMs in different ways, not just to classify a single word, but also like Tian and colleagues, they used LLM to identify the source and target domains via a 3-question prompt. And then if the domains are different, then the model classifies automatically a word as metaphorical. But the issues remain in this literature. They follow very much in the same footsteps of the previous NLP studies. So they inherit the same limitations. Decontextualized sentences. Models judge single isolated sentences. And this is a problem in the sense that even if you look at the MIP procedure that everybody seems to or claims to be using, the first thing the MIP procedure says is read the whole text to get a general sense of the meaning. So looking at individual sentences outside of context is not at least the way that humans understand metaphor, and it kind of goes against some fundamental ideas about how metaphor works in text and the ideas of cohesion and coherence and logogenesis of metaphorical meanings across texts. Again, NLP studies that use LLMs tend to focus on words, single words, but the problem is that so many metaphorical expressions are not single words. So we're missing a lot of actual multi-word expressions here. So that means that so far the task of metaphor detection has been reduced to a narrow engineering benchmark, and it doesn't produce actually usable data for linguists. And maybe for NLP people too, but like for linguists, what we need is a large annotated corpus. that is something that can be useful to ask those big picture questions that I mentioned at the beginning. What do you do with single sentences? Linguists won't find that particularly useful, and I suspect other people who are interested, outside of linguistics, people in the social sciences, people in political sciences, people who want to study metaphor in discourse won't find it useful either. So that's where we come in, and this is the motivation for our own study, where instead of looking at single sentences, decontextualized sentences, we are testing LLM's ability to identify metaphorical expressions in whole texts for the first time. So we are also comparing three methods. We are comparing retrieval augmented generation, prompt engineering, and fine-tuning. I'm sure that you all know what these mean, but I will go into a bit more detail in a second. We are comparing 10 of the most advanced closed and open source models at the time of running this study. Obviously, things move very fast in this space. And as the gold standard, we're using a manually annotated corpus of film reviews that we created, that I should say Sarah and Jeanette created, spending lots of time carefully annotating it for a previous study. And all of this, all of the data, all of the scripts, all of our results, everything is open source, and we would warmly invite everyone, and so especially in the NLP community, to take it and play around with it and see what you can do with it. So the data set is out in the public domain, and we would love for this data set to be used by others, because we'd love to see. I think there's so much potential, but luckily we had Wei Hong as part of our team, but some more techie people could really take this and make it even better, I think. Anyway, so all of the experiments were conducted obviously via the API, which enabled us to run everything very efficiently. Okay, so let me walk you through the different methods that we tried. So three approaches, as I said. The first approach was retrieval augmented generation. And this is where, in addition to a simple prompt, we are giving the LLM the detailed code book that we created to guide our own manual annotation of the corpus. This is also freely available online. And this, as you will see if you download it, this is like a thick document. It has it's like 10 pages of rules and examples and special cases and everything you need to know to replicate our annotation of the corpus. So in the system prompt, we then we prompted the LLM to take on the persona of a linguistic expert trained in metaphor identification. And we asked it to identify and label metaphorical expressions using simple XML tags. And we asked it to refer to the code book to make choices. So this is our system prompt, the user prompt. Very simple. Can you please identify and type the metaphors in the following text? And obviously we applied this to every text programmatically. All right, so then in prompt engineering, that's the second approach that we've tried. We had three different variants of the prompt. The first and the simplest variant is the zero-shot prompt, where we essentially are just asking the LLM to do the same thing as the RAG approach, but without the help of the code book. So we just ask the LLM to identify and annotate metaphorical expressions in text, just drawing on its own internal understanding, knowledge, call it whatever you like. And then the second variant was a few-shot prompt, again, super standard approach here. And here, in addition to the same system prompt that we use in the other examples, we also added either 4 or 8 examples from our gold standard corpus. And the reason why we had 4 or 8 is because we wanted to see whether that makes a difference, whether the amount of examples does make a difference. And so we laid out as standard practice, we laid out these shots, these examples as user assistant pairs. And then the final round was an open question with the plain text for the model to annotate. The third variant of prompt engineering, the third strategy we used is so-called chain of thought prompting, which in addition to providing examples also included explanations for all of the metaphorical expressions included in such examples. To generate these explanations, we used a template. So we generated these using ChatGPT, and we used the same template, and then we manually reviewed and corrected any explanations that were off. And we only made tiny adjustments. So that in itself was impressive. The degree to which ChatGPT was able to produce really clear and really accurate explanations for the metaphorical expressions in our examples. So metaphorical understanding, if we can call it that, seems to be extremely good already, possibly better actually than metaphorical identification, as we will see in a minute. Anyway, so we did this, and the idea here is that the model can learn in context, not just from the examples, but also from the explanations. All right, so that was prompt engineering. The third approach that we tried was fine-tuning. And here we fine-tuned our models using 80% of our film reviews corpus, leaving 20% out for testing. And obviously, we did this multiple times so that the testing the test set was different every time. Wei Hang would be able to explain this a lot better than I've just done, but we took all of the appropriate sort of precautions to make sure that we weren't overfitting our model, if that's the right term. Not even sure. But anyway, you get what I mean. The difference between prompt engineering, RAG, and fine-tuning is that the model itself is changed. The parameters are changed. So and that's a considerable difference. All right, so let me show you some results. These are all in the paper. The paper, of course, is I'll show you the QR code again. Paper is out. You can find a lot more detail there about all of our techniques. All the prompts are also available on our GitHub page. You can replicate our study. You should be able to replicate this in a straightforward way. But here are our results. So as you can see here, what we found is that fine-tuning was the most successful, the most reliable method, with a best result of 0.79 F1 score. So that was achieved by GPT-4 Mini. And it's kind of interesting to see that the mini version of the model was actually better at doing this than the larger versions of this model. Prompt engineering wasn't too bad either, with an F1 score of 0.74 with O3, the reasoning model O3. As you can see here, closed source models were also much better than open source models, but these were all quite small models. So we were interested in trying out local models because of potential security reasons, potential privacy reasons. In a follow-up study, as I will explain later, we've got around this issue thanks to investment made by our university here on a platform that enables private access to large full-fat models. And I'll tell you more about that later. But of course, ideally, open source models are are better because it's more replicable, because of all the reasons that we all know very well. But here they didn't perform very well at all. Now, if we zoom in on prompt engineering, we can see that the chain of thought prompt was the best performing prompt with the best result of 0.76 F1 score. Now, this is a very promising result because with prompt engineering, unlike fine-tuning, you only need a handful of examples. You don't need a full corpus. Even though our corpus was relatively small, it was only around 60,000 words, it still took weeks, probably a couple of months to annotate. So that's a lot of work, and ideally, we don't want to do any of that work anymore. Anyway, so after we checked the quantitative results, and in the paper you will find a full beta regression analysis, and all the main findings are statistically reliable. We took a thorough look at the LLM output, and we wanted to see what kind of errors the LLM made. And so now I'm going to switch over to my colleague, Sarah Turner, who will walk you through the error analysis.
Thank you very much, Matteo. Just to check, can everyone hear me okay? Is my microphone working?
Yep, sounds good.
Amazing. Thank you very much. There's always that moment, isn't there, when you switch over and you think, oh, okay. Excellent. So yes, as you see from the table that we have on the slide here, we were able to go through the errors. And I think even that word error maybe deserves a little bit of unpacking. You see at the top of the table there, we've changed it into discrepancies. So we were interested in seeing where the models differed from the judgments that we as human coders had made. So you see at the top, we've got false negatives and false positives. So false negatives would have been where the model did not code something as metaphor that the human coders did. And then, of course, false positives were examples where the model coded something as a metaphor that the human coders did not. So we went through and we had a look at all of these discrepancies, and we were able to identify some recurring kind of qualities of those discrepancies, where we were looking at it and attempting to, propose some reason for why there was that discrepancy. And you'll see them here, and we'll see some examples in a moment, but the main ones were things like decomposability, degree of conventionality, difficulties in perceiving a source-target distinction. So as Matteo was saying earlier, looking at kind of traditional metaphor identification procedures, they tend to work on this idea of, does the word have a different meaning, which is maybe more basic or more concrete, to the one that is being used contextually? And is there that kind of relationship of kind of comparison that can be drawn between the two? And in some cases, there were difficulties in perceiving whether that kind of distinction between source and target was sort of big enough to really call it a metaphor. Explicit comparisons were an interesting one, and we'll see some examples of those coming up in a moment. But also the ways in which metaphor, and again, Matteo alluded to this earlier when he was talking about the form-function debate in metaphor, but also in kind of pragmatic research more broadly, the extent to which the grammatical structure of a sentence may cue or kind of encourage or discourage metaphoricity. And that was also a source of quite a few discrepancies. We also saw confusion around other types of figurative language. Again, that's something that I'll speak to in a moment, particularly around personification. So the extent to which personification metaphor is indeed a metaphor. And interestingly, that's something that kind of coheres with metaphor research as well. There's been quite a bit of debate about the extent to which personification is metaphor. Letty Dorst is a big name in that field. Also around the extent to which metaphor works at the level of the phrase versus the level of the lexical unit or the level of the word. And again, Matteo spoke about that earlier. So as you see from this table, there are some kind of, sorry, just move my mouse pointer out of the way so I can see what I'm doing as well. So there are some interesting patterns that seem to be occurring. So for example, again, we'll pick out some of these in a little bit more detail. The idea of conventionality seemed to elicit more false negative discrepancies. Yes, thank you, Matteo. Let's have a look at some examples. So we tended to see that where the models did not pick up on metaphors that the human coders did, a lot of the time this was because these were considered to be very conventional metaphors. So for example, here we've got in the very near future. So in English, as I'm sure you're all very aware, we tend to talk about time by likening it to space. So if something is tomorrow, it's in the near future. If something's in 10 years' time, it's in the distant future or the far future. And we also use kind of spatial prepositions to talk about time. So on Saturday or at the weekend. This is something that the model did struggle with quite a bit. So it would tend to look at something like the very near future and say, yeah, no, that's not a metaphor. I mean, the other interesting point that we could make here is that, yes, a metaphor researcher would look at that and say that's metaphorical. We're using a spatial metaphor to talk about something temporal. But it's interesting to note that there isn't a literal alternative to that. There isn't really any other way that you can talk about that without drawing on that time is space kind of metaphor. And that might be another reason for why the model slightly sort of got a little bit worried about those. Interestingly as well, we saw a lot of metaphors here around size, shape, and containment. So things like, there was one example where a review was talking about the film containing a particular idea or a particular plot. Again, the model did not perceive that as metaphorical, whereas we as human raters did. Personification then, I mentioned this earlier, that's the next one. This was an interesting one again. The model appeared to miss metaphor that could be considered to involve personification. So in this example here, the fury Mother Nature can unleash. The human coders looked at that and saw nature as being personified as a human, a female human in this case, capable of expressing emotion. The model, however, did not. So the third type, false negative, was, I believe, explicit comparisons. So the model would look at an example like this, about as funny as a root canal, and would not code this as metaphor. Now, one potential reason for this is that the model may have looked at this and said, well, that is far closer to being a simile than a metaphor. However, from a sort of metaphor identification, a human metaphor identification point of view, most metaphor identification procedures would not draw a distinction between metaphor and simile, although one notable exception would be the MIP-VU procedure, which does draw a distinction between indirect and direct metaphors, just to capture that difference. But crucially, they're still metaphor. They're both still coded as being metaphor. So one of the reasons for this also is that similes, yes, okay, they're flagged, something is like something else, something is as something else, or it is as if something is something else, but they're still working on much the same principle. There's still that relationship of comparison between two distinct domains with that kind of comparison between them. So we as human coders would not consider these to be kind of special in any way. That's still a metaphorical comparison being made. The model, however, potentially thought that was a simile rather than a metaphor. What's next? Thank you. So in terms of these grammatical uses that cue metaphoricity, again, this was an area where the model did tend to miss metaphors that the human coders had identified as such. So this is an idea that kind of goes back to Alice Dignan's work back in 2005, that grammatical structures tended to cue metaphoricity. So we see here, I found this approach to be very clever. When the word approach is used as a noun, it tends to be metaphorical. when the word approach is used as a verb to approach something, it tends to be used more literally. Likewise, with the second example here, she was bathed in soft light. When the verb to bathe is an active, it's in the active form, so she bathed in the sea or something, it tends to be like literal bathing. When it's passive, she was bathed in soft light, it tends to be metaphorical. Again, the model tended to miss this, so would have coded both of those as being literal. So those were the false negatives. So cases where the model did not code something as metaphor that we as human coders did. There were also some discrepancies that occurred in both directions. So where it was a source of kind of disagreement between human and model, but didn't really skew towards one type or the other. And the reasons for these tended to be, one of these. So the first was this idea of, finding it difficult to perceive a source or target distinction, and also sort of as a bit of a corollary to that, a confusion between whether there was indeed a suitable kind of source or target that could be identified. So we see an example here where we've got a movie which is being described as being a prime candidate to join the list of high concept bad movies. So we're interested here in that expression, to join the list. In this case, the model coded it as metaphorical, and the humans did not. So in this case, we could think of the human coders as looking at this thinking, well, yeah, but there might actually be a physical list. This reviewer might actually have a bit of a list of their worst high concept movies, and this is a prime candidate to join that list. The model, on the other hand, might have thought, well, yeah, but there isn't a list. And even if there is, it's not an official list. So there is some kind of metaphorical comparison going on there. So again, a little bit of a source of contention there too. We also saw a lot of confusion in what we might call kind of twice true metaphors, where something could actually be literal in the context or metaphorical. So a nice example of that was about the horror film Alien, where a review talked about it as being a dark, enclosed horror film. I mean, that dark could be metaphorical, right? It's dark in tone, it's dark in quality, it's dark because it's a horror film. It's also literally kind of dark. So again, what do you do with that? Is it a metaphor? Is it literal? Again, that was a source of some confusion between human and model. We've talked about this idea of metaphors operating at the level of the phrase, and also this sort of relates to this idea of metaphors which are cued by particular kind of grammatical structures as well. So a second reason for those discrepancies that might have occurred in both directions were where that kind of metaphoricity lay. So in this idea of I think this was a film, being a member of that undistinguished club, it might even have been an actor in the film, I can't quite remember. The model coded the word club as metaphorical, just the word club. The human raters coded the whole phrase as metaphorical. And again, this doesn't seem like a particularly important distinction, but if you're looking at metaphor coding to look at sort of metaphoric density in a text or something like that, that difference of 5 words can be quite a lot and can sort of stack up relatively quickly. So moving on now then to the principal reasons for false positive discrepancies. This is going to be a quick one because there was really only one main sort of linguistic reason that we could identify for these examples where the model had coded things as metaphorical that we did not. And this was around difficulties that we as human raters had in perceiving a contemporary relationship based on comparison between source and target. An example here would be the idiom a red herring. Sure, it's not really literal. There are no literal red fish floating around, we hope. But we as human raters would not be able to sort of identify any kind of source-target comparison that makes that metaphor meaningful to a 20th, 21st century reader. So because of that, we probably would not have coded that as metaphorical because of that structure being, sort of lost to the sands of time, really. The model, on the other hand, did. I think it would have maybe been quite interesting to ask it to sort of go back in the etymology and tell us why that was. I suppose there's one final point to be made about this type of discrepancy here. And that is that, yeah, I mean, some of the so-called false positives, some of these discrepancies were indeed due to human error. So when we went back and we looked at our coding and we compared it to that of the model, we thought, yeah, we missed that one. That is a metaphor. That should definitely have been in there. And that kind of goes back to what Matteo was saying earlier about how in some cases we could argue that some of these models may even be performing better than human coders, because they can code for 4 hours straight. They don't need to, but they can. They don't need to take coffee breaks or sleep or do any of those other things that might sort of lead to errors in human coding. So yeah, that's our little summary then of the main discrepancies, where they came from. I think if I'm right in my recollection, I think I'm handing back over to you now, Matteo. Is that right?
That is correct. Yeah.
Excellent.
So with just some final thoughts. So yeah, thank you very much, Sarah, for that. So what can we conclude from this? First of all, well, what I think we can say based on our results is that state-of-the-art closed source LLMs can identify and annotate metaphor in full text with a high level of accuracy. 0.79 is far from perfect, but is, at or above the level of the previous NLP studies, which were based, as you'll remember, on individual sentences. This is a much more complex task. More importantly, I think the discrepancies, as Sarah has really clearly shown, are not random, but they actually point to well-known gray areas and ontological challenges in metaphor analysis that can be motivated, that can be explained, that can be interpreted. And this really points to the usefulness of LLMs as co-annotators and as potentially tools that can be used to do intercoder agreement, especially knowing how hard it is to find people who volunteer for that tedious task. So LLMs do offer a viable means of at least semi-automating metaphor identification and annotation that could be used as a first pass for creating these resources, and then the human coder could go in and check the coding and improve the coding. Comparison of human and LLM output can also help us refine metaphor theory by throwing up all these questions that Sarah explained. And lastly, I think, as I said before, our study is, as far as we know, the first to try this task on full text, on full texts, and so we hope that, or we're curious about what you think, whether this could be used as a new benchmark for NLP, moving beyond the usual data sets and tasks that have been explored so far. Okay, so the paper is out in Applied Corpus Linguistics. All the code is available on Wei Hung's GitHub. We have annotated Jupyter notebooks to walk you through all of the steps in our analysis. I don't think I have time to talk about the follow-up study, but I can answer any questions you might have about it. And in this study, we are testing the difference between the MIP procedure and the phraseological procedure, whether that influences the LLM performance and which of these procedures leads to better results. I can tell you more about it if you're interested, but I don't know. We only have a few minutes for questions, so I'll just shut up now and see if you have any questions. But thank you for listening, everyone.
Thank you very much.